All right. Before we get into the new topic, a couple of announcements. We released the Lab 1 grades on, I don't know when I did that, maybe Thursday, maybe Friday. I'll give you the chance to resubmit just Lab 1 for this Friday. So this Friday, there's 3 things that are due. There's gonna be, well, potentially 3 things. There's Lab 3 worksheet. Videos are already up. So it's just the normal lab session, just like the previous 2 labs. You can either come to the Q&A on Friday, you can do it ahead of time, but you have to submit the worksheet before the end of Friday. So that's one thing. The other thing is Lab 2 report. And the other one is, if you want the Lab 1 report, you get a chance to resubmit that one. I think that's what is due this Friday. Then this past Friday, the homework 1 was due. I didn't get many questions, so I'm guessing that that one was somewhat clear. I posted homework 2 yesterday to the Brightspace. So yeah, hopefully it turns out okay. If you have questions, you can come to my office hours. It's similar to the one from 2 years ago. I made a couple of changes, especially one problem is very different. So I'm guessing you have a lot of questions for that problem. That's it. That's the other thing I did. And the other thing is office hours for the lab. So in addition to the Q&A on Friday, we have office hours. And now I forgot, Tina, what were the office hours?
I read for class. I think Wednesday is.
Let me just check. So yeah, office hours for the lab are gonna be, I'll make an announcement, but just to let you know here, Mondays 10:30 to 11:30. So I have office hours in my office, but if you have lab office hours, so abacus questions, Tina will be holding office hours today from 10:30 to 11:30, and Wednesday from 12 to 1, in case you cannot make it during the right after class period. And then Fridays is either the Q&A for the normal lab session or office hours for lab at 9:30. So instead of at 10:30. So normal lab days from 9:30 to 1:30, and then non-lab days after class. Any questions? I think those are the big announcements. All right, yes. Oh, the computer, the same, well, I don't know the name of the classroom. 3021, yes, the computer lab in the 3rd floor. Any other questions? All right, so let's get started with today's topic, Gauss quadrature. I haven't introduced this. This is from last time. I should delete this. We haven't seen this. Yes, this is, ignore that slide. I'll delete it. Instead of that, I'll do a little bit of recap of, all I need is the weak form. Again, just to give you a little bit of a recap of what we did. This is the map. I should have this map every slide. We have the strong form to weak form, right? And then there's one homework 2 problem that is based, 2 homework 2 problems are about transforming the strong form to the weak form. And again, this is just a step that you need for the FE to work, because the FE works with the weak form. And then the other thing that we started doing last week was FE interpolation. Because we said that the best way of interpolating functions is to define these shape functions, which can be, linear, quadratic, etc., but some set of shape functions, which we call Ni, and they can be, the linear functions look like that, and they're called hat functions. linear, quadratic, etc. Such that if you have some points that describe the values of the function, we call them UIs, then we can interpolate between those UIs, and we call that UH of X, and I'll just make it explicit that the shape functions are the only things that are functions of X. The other one are just these values, these UIs, which you can think of as dials. And then the interpolation of the function is the sum of the nodal values, the UIs, times the shape functions. So that's what we were doing last time. In particular, I showed that these are defined per element. Well, I should say they could be defined globally, but one thing that we do in FE is for modularity, define Ni per element. And so, for example, you usually interpolate or plot by looping over the elements. And do operations per element. And so these were the main concepts from last week. How to define these shape functions in a very robust way. We did it for the linear, we did it for the quadratic with these Lagrange polynomials. Then how to actually use these functions to interpolate. And so that I did a little bit on Wednesday, and then we did a lot more on Friday, where I asked you to code basically the linear shape functions and plot the interpolation over some domain. And this was the main concept for that. This UH as the sum of the shape functions times the nodal values, and the fact that this is done per element. So for homework 2, I think the first 2 problems are strong form to weak form. But then the third problem is about interpolation with shape functions. Actually, the third problem is basically, I give you a mesh of quadratic elements and I give you a bunch of nodal values. And what I want you to do is to plot that interpolation. I asked for one more thing in the homework, which is what we're gonna talk about today, which is this idea of the parent domain. So this is where we are. And so today, we're gonna introduce 2 things, 2 concepts. One is, do I need to define the shape functions in terms of the X coordinate? And the answer is no. We are gonna introduce something called the parent element. And also the isoparametric concept. We'll talk a little bit about that. And so the idea for this is even more modular. Why? Because we're gonna map an arbitrary element to a single element geometry. And that is going to be useful because then the shape functions are always going to be the same. So useful because the shape functions are always the same. So no need to adjust shape functions. So it's even more modular than what I talked about last week. course, it has its own complications. And the other thing that we're going to introduce is that the concept of numerical integration or quadrature. And the reason why we need numerical integration is because if you recall the weak form, the weak form looks something like this, you know, the integral over omega of the du dx times dw dx times some stiffness, and then minus the integral of over the boundary of some wt. I forget the signs may be wrong. And then integral of w times the body force. These terms appear on the weak form, and they are all integrals. So we need to be able to do integrals. And similar to the idea of PDEs, we don't want to solve the PDE analytically. Maybe you also don't want to do the integral analytically. So how can we approximate the integral? That approximation is numerical integration or quadrature. And you have probably seen a little bit of that. Simpson's rule, midpoint rule, no? Have you done any of that in your classes? No? Well, we'll do it here. But there's some, it's basically chopping a function into small pieces and then adding them up. It's pretty much the opposite of what you do to describe an integral, which starts with chopping the space on their function into blocks and then doing the limit where the slices go thinner and thinner. Here is the opposite. We're actually just gonna chop the function into small slivers and then add them up. All right, so consider the following integral. We have some f of x that we want to integrate between a and b, and we want to know what that is. So instead of computing the integral analytically, we would like to compute the integral numerically. That is by evaluating f of x only at a few locations and then adding them up. This is called quadrature. What is the simplest form of quadrature that you can think of? Would be to just select a few points, right? So this is some x1, some x2, some x3, some x4, x5, and x6, and the corresponding function values. So this is the function evaluated at x1, the function evaluated at x2, the function evaluated at x3, and so on. And then associate with each of these functions a little rectangle. Obviously, the height of that rectangle is the value of the function. And the width of the rectangle is, let's just call it this dx1, dx2, dx3, and so on. So this integral is approximately the sum of the area of each of those rectangles. So the sum over I of the function value at those xi times the width of the rectangle. So times delta xi. You can see it's pretty much the opposite of what you did for defining the integral. So that means that you actually don't need to do the analytical computation. When the integral is just evaluate the function at a few locations and then add them up, multiply by the width of the rectangles that you are considering. And there's some variations of this, the Simpson rule, midpoint rule. There's some specific ways in which you can choose these xi values at which to evaluate. But this is the main idea. Now, there's one set of points at which to evaluate and corresponding widths of the rectangles that give you a very nice sort of bang for your buck in terms of accuracy of the integral, because you can imagine that how you pick those points at which to evaluate and sort of the different size of the rectangles affects how accurate your integral is. Obviously, the easiest way is just evenly spaced points, and that works fine, but typically requires a relatively large number of rectangles to evaluate. And this was investigated, hundreds of years ago for what is the optimal way of doing it. And so Gauss came up with a way of selecting points in the -1 to 1 range. So when you have a function that is between -1 and 1, there is optimal points at which to evaluate and optimal widths of the rectangles that best approximate the integral. And that is called Gaussian quadrature. Quadrature is the same as numerical integration. I actually don't know what the origin of the word quadrature is. I don't know if it has to do with the fact that you have these little rectangles. But Gaussian is because of these points that found by Gauss. If you Google it, you get to a Wikipedia page. And this means that you don't have to think about where to evaluate the function. This immediately tells you what are the optimal points and the rectangles that you need to consider. So if you have only one point to evaluate, this is sort of your buck here, your budget for how many function evaluations you want to do. If you can only evaluate the function at one point, then this one is pretty intuitive. Where is the best? Well, the best is just to evaluate at the center at 0, and then have a single rectangle of size 2, and basically get that area. So that is if you have only one single point, then this is the best that you can do. That one is intuitive. Actually, let me do it in a different, just do it down. So 1 point Gauss. So again, if you have a function between -1 and 1, 1 point Gauss means that all you need is to evaluate at the center and then consider that rectangle. And then the integral between -1 and 1 of that function is approximately 2 times the value of the function at 0. The 2 comes from the base of the rectangle and is this weight in the table. And the location is 0. Again, that's if you only want to evaluate the function at one point, this is the best that you can do. Now, let's say that you have 2 points to evaluate. Again, it's the same function between -1 and 1. And it's the same integral. I still have the integral between -1 and 1. But now let's say that I want to evaluate at 2 points. Then if I just look at my table, the table just says the optimal points are these 2 points. or in decimals is minus 0.5773 and 0.5773. So that just means that based on my table, I should evaluate at minus 0.577, etc., and at 0.577. And then the width of the rectangle is whatever is given here, which is 1. So each one of these is 1. So here is 1 times f evaluated at minus 0.577 plus 1 times f evaluated at 0.577. Again, that's the best that I can do. If I have 2 points at which to evaluate, I'm just gonna illustrate this, but I'm not gonna do all the details. So if I have 3 points to evaluate, I don't even gonna look up the points. But there's 3 points. I don't know what they are, but there's some point x1, x2, and x3 just from the table. And the corresponding width of the rectangle, I also don't know what it is, but it's wi from table. So that the same integral is going to be approximated by the sum of, in this case, this is a 3-point Gauss, so from 1 to 3, of the wi, which is again this width of the rectangle from the table, whatever that is, times the function evaluated at xi, where xi is the points from the table at which I need to evaluate. So for 3-point Gauss, I'm gonna guess that x2 is the middle, 0, but I don't remember what x1 and x3 are. But again, this is just follow the table. So yes, there's 1 point at 0, and that one has, you can see here, for example, that the rectangles, these weights, don't have to be the same. So it's not the most optimal to always have equally spaced rectangles. This, the 3-point set of optimal points and weights, tells you that actually the middle rectangle should carry more weight. You see that the middle rectangle is 8/9, which is bigger than the other 2 rectangles. And again, you don't need to worry about where this comes from, but these have been optimized such that these tell you what the best points to evaluate at and the best widths of the rectangles. Any questions about that? Yes. Oh, we'll do that on the lab on Friday. Do you do reduced integration elements on Friday? I don't know if in this one you do. Maybe not in this one, but in, yeah, probably the next lab. But so typically depending on the polynomials that you use, the more points you need. You can imagine that if you have a line, that is very easy to interpolate that, to get the integral of that line. So you probably don't need as many points to evaluate. So you have a line with 1 point, the 1 Gauss point gives you an okay result, 2 Gauss points for sure. If you have quadratic, 2 Gauss points. If you have cubic, so because the higher degree of the polynomial, the more wiggly it looks. And so then the more rectangles that you need to actually integrate. So it depends on the element that you use. For linear elements, usually 2 points. For quadratic elements, 2 or 3 points. Yeah. Any other question? All right. So we'll code it eventually. Maybe on Wednesday, I'll do a little bit of coding to just show how this translates directly into code. But there's one thing that we need to solve, which is that this table, that if you look it up, is only defined for functions that you want to integrate between -1 and 1. And that is a problem because for our mesh, if you think about the things that we have plotted, and we have this, yes. So that is the next thing. This is a problem, right? Because you can imagine that typically an element, if you have some element, that element does not necessarily have to be between -1 and 1. That element can be, 4 to 6. Actually, you have many elements, right? So you have a mesh that, maybe I'll draw it here. So let's say problem. This only works between -1 and 1. But if you imagine a mesh, in X between, say, let's just keep the notation A and B, right? So we have done where you have, a bunch of elements. Let's say these are linear elements. And this is from X equals 0. This is X equals 1. This is X equals 2. This is X equals 3, for example. So in this case, there's some mesh with 3 linear elements. So 3 linear elements. Between 0 and 3. So now that's a problem, because let's say I have some function that I want to integrate. How do I use my Gauss points for a function that is not between -1 and 1? And this is where the other bullet point that I had at the beginning comes into play. We can map any element to a -1 to 1 element. That -1 to 1 element is called the parent domain or parent element. So that's the second thing that we need to be able to do. And this is the map. So we need a way to map any element that is in terms of X between A and B, where A and B can be whatever 2 numbers. And I need to map that to an element. It's just a change of variables. I just need to change variables between X and this new variable called psi, such that this psi is always between -1 and 1. So can I define a general way of doing this mapping? This is called the isoparametric map. And there's linear, quadratic, etc., depending on the shape functions that you use. For the linear case, you can see that I'm putting X in terms of psi. So this is a relationship between the two, such that if I put in any value of psi, if you invert this map, you can do the opposite. But here, actually, the map goes kind of like this. The way I define it, it goes like this. And it's basically, if I pick any value of psi between -1 and 1, I can get the corresponding X. So if I pick, let's say psi equals -1, and I put that into this equation, what will I get? You can do the algebra, you will get x1e. So that means that the point that is at psi equals -1 will get mapped to the point x equals a. I do have extra space for that. So pick any psi, get the corresponding x. Pick psi equals -1. You can evaluate it. You will get that x equals a or x equals x1e, depending on how you label this. I label here either with x1e or with a. They are the same. If you put in psi equals 0, what do you think is the x that you're gonna get? The half of a plus b, yes. Then you're basically gonna end up in the middle of the elements. If you put in psi equals 1, obviously you're gonna get the other end. You're gonna get x equals b. But you can pick any value of psi between -1 and 1. If you pick psi equals -0.5, then you'll get some point. I'll just do it with an x. So you pick a value here for psi, and you evaluate this equation, either the top or the bottom one. You end up with some x value that is somewhere closer to a than to b. Again, this is nothing but a change of variables. But this is the key to do the integral. So I have space, I don't have space, I'll derive it here, okay. So now let's do the integral. So you have an integral between a and b for f of x dx. Can you tell me what the integral is if I want to do it between -1 and 1 d psi? Any takers? Any brave person that remembers this from your calculus? Yeah, that's one thing. That's great. So f of x of psi, yes, and one other thing. What other thing? There's one other thing that you need to do. But that is definitely one thing. Just replace x with x of psi. No, I'm sure you did some change of variable for integrals in calc classes. No? Any wild guess? I'm missing something here. Yes, it is the derivative of the map, the derivative of x with respect to psi. So this is typically abbreviated with Jacobian, which is the derivative of the map. So this is called the Jacobian, and it comes from the fact that you want to relate dx to d psi. They are not the same. So dx and d psi are not the same. This is the derivative of the map. So this is the derivative of the isoparametric map. So if you recall what the x was 1/2, I forgot now what it is, a plus b plus 1/2 b minus a, 1/2 b minus a of xi. If you take derivatives of both sides, you will get that dx equals 1/2 b minus a dxi. This is the Jacobian. Alternatively, you can just do dx dxi and then just take the derivative on the right hand side, which is just 1/2 b minus a. But yes, these are the two changes that you need to do. All right, so just to wrap it up, let's just do an example. Let's say I have some function, well, let's say I have some domain x, this is a single element, and it's between, let's say, 2 and 4, and I have some function given directly in terms of x squared minus 1. And I want to approximate, I want the integral between 2 and 4 of that function. But I'm gonna approximate it with Gauss quadrature. So what I need to do is I need to map this 2 to 4 to this minus 1, 1. I should do it with like dotted lines. Isoparametric map. That map is just like I said before, x equals 1/2 a plus b, so 1/2 2 plus 4. I'll write it and then I'll substitute the plus 1/2 b minus a xi. In this case, 1/2 of 2 plus 4 plus 1/2 of 4 minus 2 xi. Whatever that is, this one is actually 3 plus xi. That's my map. The other thing that I need is, so map between xi and x. I will also need the Jacobian of the map, it's just the derivative. So I just need dx dxi. In this case, this is just 1. Then I can set up my new integral. It's just, instead of the integral from 2 to 4, this is, here there's still an equal sign. This is the integral between minus 1 and 1 of f of x of xi times the Jacobian, which is just 1, times dxi. Now that integral is between minus 1 and 1. Actually, let's call this g of xi. So you can see that this now looks like now that looks like something that I can do with the Gauss quadrature. So approximate. So let's say that we're going to use the 3-point Gauss. So then, again, I'm gonna keep this whole chain of things. So all of that equal, equal, equal. Now this is approximately equal to W1, which I'll get from my table, times G of Xi1, again, Xi1 I'll get from my table, plus W2 times G of Xi2, plus W3 times G of Xi3. Where this W1, Xi1, W2, Xi2, all of those come from table. These are just numbers. W1 is 5/9. Xi1 is, I forgot what it is. It's like minus square root of 1/5 or something like that. I don't remember. Just look it up. Again, the approximation is here. Let me just do one extra thing. So this last thing equal to, I'll be a little bit more explicit. What is G of Xi1? How do I evaluate G of Xi1? The W1 is just a number, so that one is easy. But G of Xi1 means evaluating f of x of Xi. So that would mean f of x of Xi1 times j. Then W2 f of x of Xi2 times j plus W3 of f of x of Xi3 times j. By hand, it looks a little bit more tedious to calculate. In the computer, it's going to be very easy. What do I mean by f of x of Xi1? That just means that given Xi1, go and evaluate the map, right? So given Xi1, give me the corresponding x. So for Xi1 equals whatever it was, minus 0.7 something. Then get the corresponding x, then evaluate f at that x. Right, so what is this? This is x equal 3 plus Xi1. What is this? This is x equals 3 plus Xi2. What is this? This is x equals 3 plus Xi3. So for a given value of Xi, go get me the x. Now, once you have the x, go evaluate the f, which is x squared plus 1. So this one is W1 of f of, I don't know what this is, but it's going to be something like 2 point something. Plus W2 of f. Xi2 is 0. That one I can tell you that one is going to be 3. And then plus W3 f of, I don't know what this is going to be. This is going to be 3 point something. And that's it. You do that sum, W1 times f at 2 point whatever it was, plus W2 f of 3, plus W3 f of 3 point whatever it is. Then you get an approximation of the integral. Any questions? I think it will look a little bit cleaner on code. No questions, super clear. Again, two main concepts from today's class. One is this idea of approximating integrals by chopping your function into these squares or rectangles and then adding them up. There's efficient ways of doing it. An optimal way is with this Gauss table. And the only problem is that that Gauss table only works for functions between -1 and 1. But usually our functions are in some x that is definitely not -1 and 1. How do we solve that? We introduce this, well, what I call the parent element or parent domain, which is always between -1 and 1. And then the problem that brings us is now we need a change of variables between the xi and the x. I call that isoparametric map. If you have that map, then you can change your integral from a to b with respect to x to -1, 1 dxi. And then use the Gauss points in the -1, 1 integral. I think that's it. On Wednesday, I will probably actually code it. You don't have to bring your computer, but I'll probably show you how to code exactly this that I did now. And I'll upload the code. Yeah, see you on Wednesday.
Meaning your office or my office?
Your office.